Hello and welcome to today's lecture on supply voltage scaling. This is the first lecture on this topic. In the last 3 lectures, we have discussed about the various sources of power dissipation, and we have identified which parameters we can control, and based on that we shall start our discussion today on supply voltage scaling. And here is the agenda of today's lecture. After a brief introduction where we shall recapitulate what we have discussed in the last couple of lectures, we shall discuss about challenges in supply voltage scaling, and then various voltage scaling approaches that we shall discuss, and after that we shall start our discussion on static voltage scaling approaches, starting with device feature size scaling, after that architectural level approaches like parallelism, pipelining, and then architectural level transformations. Okay. So, first let us briefly recapitulate what we have discussed in the last 3 lectures. We have discussed about various sources of power dissipation. Sources of power dissipation in CMOS circuits. You may recall that the sources of power dissipation can be broadly divided into 2 categories. One is your power dissipation, that is your dynamic, and second is static. Now, under the dynamic sources of power dissipation, that means when the input is changing, clock is changing, we have 3 components. Number 1 is known as P switching power dissipation, and as we know this is proportional to alpha L C L VDD square F. This is the equation alpha L C L VDD square and F, plus there are many internal nodes in which you can say there are k nodes, I is equal to 1 to k, it is equal to alpha I, C I, VDD, and then VDD minus VT. This is the equation we derived, and second component is P short circuit, and that short circuit power dissipation equation, if you may recall that it is equal to k W by L, that is equal to beta into 1 by 12 VDD cube, and then 1 minus 2 VT by VDD cube, and then you have got tau into F. And third component was switching short circuit, and third component was P glitching. Glitching power dissipation is essentially same as the, it is again for the charging and discharging of capacitor. So, there also it will be equal to, it will be you can write alpha L C L VDD square per transition, and number of transitions that will occur will be dependent on the switching activity. So, these are the 3 components: P switching, P short circuit, and then P glitching. These are the 3 dynamic sources of power dissipation that we have discussed in detail. And second is your P static. As we know, in CMOS circuits as such there is no static power dissipation. That means, there is no static current flow when the input is 0 or input is high. However, there are many sources of leakage currents, as we have discussed: gate leakage, subthreshold leakage, and third one was the gate leakage, subthreshold leakage, and third was because of P gate leakage, P subthreshold leakage, and third was P, another source was your gate, subthreshold, and third component that is due to diode, reverse bias diode leakage, you can say. So, these are the three components, and the sum total of current, we may say this is your I leakage, and then P static power dissipation can be equal to VDD into I leakage. So, this will be the power dissipation due to static power dissipation, and I leakage is the sum total of the gate leakage, subthreshold leakage and diode leakage. So, if we analyze these equations, we find that the supply voltage is present in all the equations. That means, here somewhere it is proportional to VDD square, that means quadratic dependence, cubic dependence, here also quadratic dependence, and here it is linear dependence. However, this leakage current itself is also dependent on supply voltage. For example, gate induced drain leakage and various leakage currents are there, which are also dependent on the supply voltage. So, as a consequence, we find that supply voltage is the most important parameter which you can control to reduce power dissipation, and that is the reason why we are discussing we are starting our discussion on leakage power reduction starting with supply voltage scaling. That means, how we can reduce power dissipation by supply voltage, and of course, there are other components as I mentioned, supply voltage, physical capacitance, switching activity and threshold voltage. These are the other components which we shall consider, but right now we shall focus on supply voltage. Supply voltage scaling, minimizing switch capacitance and minimizing leakage power. This is how we shall continue our discussion one after the other, and first we shall focus on supply voltage scaling. Now, let us have a look at the challenge in supply voltage scaling. We know that supply voltage scaling is very important, and it has the most dominating effect in reducing the supply voltage, in reducing the power dissipation, but is there any challenge in it? Is it so simple? That means, say if you say that if supply voltage scaling gives you reduction in power dissipation, why do not you simply reduce the supply voltage? I mean, as low as possible, but that we cannot really do arbitrarily, as we shall see. This will be clear from this discussion. First of all, based on the switching power dissipation, we can say a factor of 2 reduction in supply voltage yields a factor of 4 decrease in energy. That means, energy drawn from the source will be reduced by a factor of 4, assuming that it has quadratic dependence. But another point is that what is the lower limit? How long we can reduce the supply voltage? It has been established theoretically that the supply voltage for CMOS circuits can be as low as 0.2 volt. Although this is the theoretical lower limit, in practice we cannot really reduce the supply voltage to such a low level. Why? The reason is you have to either supply the power from battery or from a voltage regulator. So, we cannot really get a power source which can supply at 0.2 volt. That is the reason why nowadays the supply voltage that is being used, minimum value is about 1 volt. However, that is a theoretical limit. Now, but one very important point is, as the supply voltage is lowered, the delay increases, leading to dramatic reduction in performance. This is what you have to take into account when we reduce the supply voltage. So, here we see as we reduce the supply voltage from 5 volt to 1 volt. So, there is reduction, and that normalized energy reduces from 1 to maybe less than 0.1. So, you can see more than 10 times reduction in energy occurs as we reduce the supply voltage. So, as I mentioned in the beginning, that if you reduce the supply voltage by half, the energy reduces by 4 times. But what impact it has got on the delay? you can see as you reduce the delay, I mean as you reduce the supply voltage, delay is increasing. What is the equation for delay? Earlier we have discussed the delay in CMOS circuits. We remember, you may recall that delay is proportional to 1 by VDD, then 1 minus VT by VDD square. There are other parameters, capacitance and various other things, but we have only considered the component which is related to supply voltage. So, you see assuming that this ratio is maintained, this the ratio of the threshold voltage and supply voltage is maintained, that means as the supply voltage is reduced, threshold voltage is also reduced. Even then we find if we reduce the supply voltage, delay increases linearly. That means delay increases linearly if the supply voltage is reduced from say from some voltage, say 5 volt to 3 volt or 2 volt. But if we consider this parameter, suppose we reduce the supply voltage without reducing the threshold voltage, then what happens? In this parameter, in this particular part, 1 minus VT by VDD, this is in the denominator, and as the supply voltage approaches the threshold voltage, this part becomes very small, 1 minus this becomes close to 1 when supply voltage is close to threshold voltage. So, this part will be very small and square of that will be still smaller, and as a consequence delay will be very large. That means, whenever we reduce the supply voltage without reducing the threshold voltage, and when the supply voltage becomes closer to the threshold voltage, there is dramatic increase in the delay, as you can see from this curve. So, here you can see in this part it is definitely increasing, delay is increasing, but here it is increasing at a very high rate because this it has become closer to the threshold voltage. So, what is our observation from these two curves? From these two curves, you see, number one is that supply voltage helps us to reduce the power dissipation, particularly quadratic reduction occurs, reduction in energy, but delay also increases if not linearly, I mean in the when the supply voltage is away from the threshold voltage, then linearly, but normally threshold voltage is kept fixed and supply voltage scaling is done. Then delay increases at a very high rate when it becomes closer to the supply voltage and threshold voltage. So, that means increase in delay means loss in performance. So, if we do a supply voltage scaling, there is loss in performance, which will not be accepted for many applications. That means, for many applications people will say yes, you can reduce power dissipation by reducing supply voltage, but we are not going to compromise on performance. So, this is the challenge of supply voltage scaling techniques. What we have to do? We have to reduce the supply voltage in such a way that there is no reduction in performance. We shall not compromise on performance. That means, supply voltage has to be done without compromising performance. That is the biggest challenge, and how it can be done we shall discuss when we discuss several techniques. Now, here are some of the categories of supply voltage scaling. First one is static voltage scaling. So, in static voltage scaling, normally we develop a technique, I mean supply voltage is reduced and that voltage is maintained. Say you have got a processor, say microcomputer, you decide to reduce the supply voltage from say VDD 1 to VDD 2, and based on the performance requirement we decide that it will operate at VDD 2, which is where we assume that VDD 1 is greater than VDD 2. So, we scale down the supply voltage and that voltage is maintained at run time. That means, when we are using the device, using the system, we do not reduce the, you do not change the supply voltage. At design time, we fixed a voltage and we maintain that. So, this is known as static supply voltage scaling, that is the significance of the term static. That means, it is not changed while the circuit is in operations, and you may have different blocks where you can have different fixed voltages. Now, second approach, which is an extension of this static voltage scaling, is known as multi-level voltage scaling. So, this is an extension of the static voltage scaling, where the supply voltage is switched between two or few fixed voltages. That means, here what we are doing, suppose you have a logic block, maybe microprocessor or some other module, where you will apply say at one point of time you will apply VDD 1 and another point of time you will apply VDD 2. So, there will be a switch which will use either this voltage or this voltage. That means, the number of voltages is very few. Here I have shown only 2. The module is applied with the supply voltage VDD 1. So, that can be changed with the help of switch, or it will switch, it will use another voltage VDD 2. That means, the supply voltage can be kept one or few supply voltages, that can be selected with the help of a switch between two or few fixed voltages. That is the basic idea of multi-level voltage scaling. So, you have got multiple voltage levels and between them it will be switched. And third technique is essentially an extension of multi-level voltage scaling MVS, which is known as dynamic voltage scaling. So, however, whenever we do dynamic voltage scaling, we also scale the frequency, because that will give you more benefit. That means, as you scale down the voltage, you also scale down the frequency. That is the reason why this technique is known as DVFS, that means dynamic voltage and frequency scaling. And here what we do, a large number of voltage levels can be dynamically applied for different workloads. That means, you can have maybe 100 different voltages that you can apply and which you can change dynamically at run time. So, this is the difference between the first two approaches. In the first two cases, we normally we do not change at run time, but in the second case, in the third case, that is your dynamic voltage and frequency scaling, dynamically at run time you keep on changing the supply voltage, of course, depending on the workload of the processor or some of the subsystem, and also you use different frequency. In other words, you will choose different voltage frequency pair, say VDD I and F I. So, this pair you will use, and the number of such pairs can be maybe 100 or more than that. So, over a large number of voltage frequency voltages, different voltages you can apply to the module, and we shall later on we shall discuss how exactly it can be done. Finally, we have another technique, adaptive voltage scaling. So, this dynamic voltage and frequency scaling is essentially a open loop technique. By open loop we mean at design time what voltage can be applied, what frequency can be applied, these are decided based on based on the worst case performance for the very worst case performance requirement. Whenever you change the PVT parameter, voltage and temperature, overall that PVT over when the parameter varies because of different reasons, voltage varies at run time, temperature varies at run time. Under such conditions, it will it has to work. That is the reason why this approach, this dynamic voltage and frequency scaling is very conservative, because the design has to be made in such a way that under worst condition of process voltage and temperature variations it will work. But obviously, whenever you want to do that, the design has to be very conservative, and as a consequence the benefit that you get is not really optimized. So, on the other hand, in adaptive voltage scaling, it is essentially a closed loop technique, where at run time the behavior or the performance of the circuit is monitored with the help of some on chip circuit, and based on that the voltage and frequency are decided. How it can be done, that we shall discuss in detail. As a result, you can say this is a closed loop voltage and scaling, voltage and frequency scaling technique, and that is the reason why it is called adaptive voltage scaling. So, it keeps on it adapts the changes that occurs because of changes in parameter values, changes in because due to the change in voltage, due to the change in temperature, and so it keeps on adjusting the voltage and frequency because and with the changing of workload. So, these techniques we shall discuss one after the other. Of course, today we shall start our discussion on static voltage scaling. So, first we shall start our discussion on device feature size scaling, and then we shall focus on architectural level approaches. What do we really mean by device feature size scaling? As you know, because of the advancement of VLSI technology, advancement of photolithographic techniques, the size of the devices that you can fabricate is gradually reducing. For example, here there is a chart and here is the feature size in micron, and on the first row is giving you the year. So, in the year 1985 the feature size was 2.5 micron, that means this was the lambda value, 2.5 micron was the lambda value, that was the minimum feature size. So, the devices minimum size device was 2 lambda by 2 lambda, that means if you fabricate a device, it has to be minimum size will be 5 lambda by that 5 micron by 5 micron, that was the minimum size. But you can see over the years how the size has changed. In the year 1987 it becomes 1.7 micron, and in 89 1.2 micron, in 1991 1 micron, and in this way over the years it has reduced, and in the year 2009 I mean where we are now, it is now in the deep submicron era. So, you can see the feature size is 0.045 micron, that means 45 nanometer. So, we are now in the era of 45 nanometers. Nowadays, the VLSI chips are implemented using 45 nanometer technology, and you may have heard of Moore's law. Moore's law predicted this kind of reduction based on some simple observation, and that Moore's law is still followed until recently because of increased leakage power. There is a problem, but until recently Moore's law has been followed very closely, that prediction. In other words, device feature size is responsible for the success of Moore's law. What do we really mean by device feature size scaling? Let us look at this diagram. We have got a schematic diagram, 3-dimensional schematic diagram of a MOS transistor, and you have got different features. For example, this number 1 is thickness of the silicon dioxide. So, TOX dash TOX, this is the thickness, and as you go from one technology generation to the next technology generation, the thickness is reduced by a factor S. So, if TOX is the feature size of a particular technology generation, next technology generation will have a feature size which is equal to TOX by S. And similarly, second parameter ND dash, that is your doping concentration in the that source and drain regions, that is increased by a factor of S. Actually, this is necessary to maintain constant electric field. And what are the features reduced? The thickness of the silicon dioxide, then length is also reduced by a factor S. So, here the parameter 3, this is the length from here. So, this is the source, this is the drain. So, the length is L. So, whenever you go for next generation, length is reduced by factor S. So, L is the present generation, L dash is the next generation. Similarly, the depth of penetration of the device, that is the parameter 4, that is also reduced by a factor S. X j dash is the next generation depth of penetration of the devices, I mean of the diffusion, and in the present generation it is x j by S. And fifth parameter is the width, this is the width, and width is also reduced by a factor S, W by S. So, you can and finally, the last parameter substrate doping, that is increased by a factor S. So, we find that all the physical parameters, length, width, thickness of the silicon dioxide, depth of penetration of the diffusion, these are all reduced. However, the doping concentrations are increased by a factor S. So, this is known as device feature size scaling. Now, what is the impact of this? Whenever we do this, what happens? So, let us consider one very important technique, that is your constant field scaling. Constant field scaling, basic idea is that as you reduce the dimension, the electric field within the geometry of the device has to be maintained constant. That is the basic idea. So, whenever you want to maintain the electrical field constant, as you reduce the dimension of the devices, you have to maintain you have to reduce the supply voltage also. As you can see here, as you are reducing the dimension of length, L, width, channel width. So, channel length, channel width, gate oxide thickness TOX, junction depth XJ, these are all you are reducing, and to maintain constant electric field you have to reduce the supply voltage as well. So, it is VDD by S, and not only the supply voltage, you have to reduce the threshold voltage VTO, that means VTO is essentially threshold voltage with 0 body bias. So, with 0 body bias that threshold voltage is also reduced, and in the next generation it will be VTO by S. However, as I mentioned, the doping concentrations are increased by a factor S. So, whenever you do this kind of constant field scaling, then what impact it has got on the electrical parameters. So, the physical parameters are scaled down, the supply voltage is scaled down, threshold voltage is scaled down. What impact it has got on the electrical parameters, because electrical parameters will decide the performance of the device. Let us have a look at the different electrical parameters. First, let us consider the capacitance, that is your unit gate capacitance COX dash. How it is reduced? It will be reduced by a factor of COX, as you know that it is equal to epsilon OX dash by TOX dash. So, for the next generation, this will be the we know that unit gate capacitance is equal to the permittivity of the silicon dioxide by the thickness of the silicon dioxide, and this is equal to, of course, the permittivity does not change as you go to the next generation. So, this remains as the same as the previous generation. However, the silicon dioxide thickness is reduced as we have seen. So, it becomes TOX into S, or we can write it that this is equal to S into COX dash. That means, as we go from one technology generation to the next technology generation. So, this is the previous generation. So, the unit gate capacitance increases by a factor S. So, unit gate capacitance increases by a factor S, and unit gate capacitance is increasing by a factor S. Obviously, it will have impact on the gate capacitance. Later on we shall discuss about that. Second parameter, let us consider the current I ds linear. So, what is the value of I ds linear? This is, as we know, the equation K W by L into V g s minus V t into VDS minus VDS by 2 square. This is the equation for the linear, that linear current when the circuit is in the MOS transistor is in linear region. Now, I mean these are you have to put all dash here. This is for the next generation. Now, which parameters are reduced, and from this you can say and how it is related to the previous generation. As you go from one technology generation to the next technology generation, how the current changes, does it increase or decrease. So, if you consider these parameters, you will find that this will be equal to I ds by S. That means, it will reduce by a factor S. That means, the supply voltage and all these parameters are reduced. So, here you will one factor S will come out, these two will get neutralized, and K has a value, that is your mu n EOX by TOX. So, this from this 1 S will come. So, and as a consequence, here you will get I ds by S. So, this will be, this current will be proportional to I ds by S. Similarly, that I ds dash saturation, as we know, the expression is kW by L into half and VGS minus VT square. So, here also you will find that it will be equal to I ds saturation of the previous generation by S. That means, the current will reduce by a factor S. As we go from present generation to the next generation, current will reduce by a factor S. What about power dissipation? P that is equal to I into VDD. So, let us consider the power dissipation of the next generation. We have seen that current is reducing by a factor of S, I ds, we can say I ds by S, and supply voltage is also scaled down by a factor S. So, we can say that P by S square. That means, the power dissipation is reducing by a factor of S square. So, as you go from one technology generation to the next technology generation, this power dissipation will reduce by a factor S. What about the gate capacitance CG dash? As you know, that will be equal to W dash into L dash into COX dash. And in this particular case, what will happen? This will be equal to W and L. Here it will be S into W and it will be L into W. So, S square W into L, and in this it will be COX, and it reduces by a factor S. So, this will be equal to S into, and this part is your CG. So, we can see that the gate capacitance is also increasing by a factor S. Now, from this what is our observation, and of course, another parameter is there, that is your power delay product, say power into, so P into delay, power delay product. So, this you will find that power delay product will not change, because power will increase by a factor of S square and delay will increase by a factor of S square. I mean delay will reduce, that delay will reduce. So, power delay product, that is energy, will remain same, energy will remain same, as we shall see from this summary. So, we find that power density, not really power delay product. So, power density, power is increasing by a factor of S square and your area is reducing by a S square. So, it will be A into S square, this S square will cancel out. So, power density will remain same, energy will reduce by a factor of S cube. So, from this, here is a summary. The gate capacitance is reducing by a factor S, the drain current is reducing by a factor of S, power dissipation is reducing by a factor of s square, power density is remaining same, delay is reducing by a factor of s, and energy is reducing by a factor of s cube. So, we find that whenever we are doing device size scaling along with supply voltage scaling, delay is not increasing, there is no loss in performance, rather delay is reducing. So, we can say this is beneficial to us. That means, even by doing voltage scaling, the performance is getting upgraded, and in fact, as a consequence we have seen how the frequency of operation of the microprocessors has increased over the years as we have gone from one technology generation to the next technology generation. In the 80s, you may recall the microprocessors were operating with clock frequency in the range of megahertz. Now, the clock frequency is in the range of gigahertz, and this is the reason for that. So, this is constant field scaling, and there is another technique which is known as constant voltage scaling. You know, whenever we are reducing the device sizes, then feature sizes, that means length, width, we cannot always reduce the supply voltage, because there are many other subsystems which will be operating at some supply voltage. We cannot always reduce the supply voltage. So, what happens in such a situation? We shall reduce the feature sizes without reducing the supply voltage, and obviously, we shall also not reduce the threshold voltage in such a case. So, in such a case, as you can see, all the parameters, physical parameters, length, width, thickness of the silicon dioxide, junction depth, all are reduced by a factor s. However, supply voltage is kept same and threshold voltage is also kept same. However, in such a case you have to increase the doping concentration not by a factor s, but by a factor of s square. So, doping concentration is increased, the feature sizes, different feature sizes are reduced, but supply voltage and threshold voltages are maintained same. So, this is known as constant voltage scaling. And what is the impact of this constant voltage scaling on different physical parameters, different electrical parameters? You can see here the gate capacitance also will reduce by a factor s, because we are reducing the length, reducing the width, and so the gate capacitance will reduce by a factor s, and drain current will also reduce by a factor, will increase, but here you can see instead of drain current getting reduced by a factor s, here it is increasing by a factor s, because the supply voltage is more and drive will be more. So, drain current will be more, and as a consequence power dissipation is also increasing by a factor s. So, it is not really very beneficial from the low power viewpoint, and however, the most important point is power density. You can see power density is increasing by a factor of s cube. So, this is not good from the viewpoint of low power, because if the power density is large, then over a small area there will be large power dissipation, and that may lead to what is known as hot spots. So, this is not very attractive from low power applications. However, for high performance this is good, because delay is reduced by a factor of s square. So, we have seen that constant field voltage scaling is not very low power, I mean is not good for low power application, but whenever we do constant field scaling, then we can reduce the supply voltage, and simultaneously the performance is improved. Okay. So, with this we now switch to the next topic, that is your architectural level approaches for static voltage scaling. So, architectural in the architectural level what we do, that is called RTL level, register transfer level. We have got different blocks like ALU, adder, multiplier. We shall be doing the voltage scaling at this level. So, there are two approaches we shall discuss. First is parallelism, and after that we shall discuss pipelining. First we shall focus on parallelism. You are all familiar with parallel processing. Normally parallelism is used to improve performance. we know instead of engaging one leverer, if you engage two leverer, obviously the work will increase. Similarly, instead of using a single processor, if you use dual processor, performance will increase. That is the normal, normal I mean that is the convention. Traditionally, this parallelism is used to improve performance. Here we shall see how we can use it for low power. We are not interested in increasing the performance at this point, but we are interested in retaining the performance level same, and at the same time we want to achieve lower power. How can it be done? By using parallelism. So, here the key approach is to trade area for power while maintaining the same throughput. So, by when we go for parallelism, obviously it will involve use of more than one modules, more than one subsystems, and that will definitely increase area, and we shall see how the throughput can be maintained, and that will help us in reducing power dissipation. Basic idea is as you reduce the supply voltage, power dissipation reduces quadratically. That means, if you reduce the supply voltage by say if you make it VDD by 2, the energy consumption reduces by a factor of 4. But how the area increases? If you duplicate it to compensate the loss in performance because of reduction in supply voltage, then that area will increase by 2. That means, we shall see that even by duplicating, even by increasing the area, which will lead to which you may think that it will lead to more increase in power dissipation, you will see that overall there will be overall reduction in energy, keeping the performance same, because the loss in performance will be compensated by parallel processing. How? Let me illustrate with the help of an example. We have got a two 16-bit resistors, and the resistor supplies two operands to an adder. So, here is a 16-bit adder. So, we have got two resistors in the form of latch, and we have got a 16-bit adder, and here let us assume the operating frequency is 100 megahertz. So, what is the dynamic power dissipation? We know that the power dissipation is CL VDD square and F. So, F. So, for this particular full adder, this is considered to be a reference circuit. It is considered that P reference is equal to C reference. C reference is the overall capacitance of this adder, and VDD this is the reference voltage. So, V ref square and F ref. This is the power dissipation of this two adder. This is the reference power dissipations of this 16-bit adder, 2 input 16-bit adder. Now, when we go for parallelism, we shall duplicate it, and whenever we shall do the duplication, what will happen? The circuit will look like this. That means, we shall be having two different 16-bit adders, two separate 16-bit adders, and they will be applied these two operands A and B, and you will be doing some kind of time division multiplexing. That means, you will be applying to this, then to this, then, and also you will take out the output with the help of a multiplexer. So, this is somewhat similar to time division multiplexing of the two adders, and where we are applying inputs alternately, and we are taking the output with the help of a mask, with the help of a multiplexer. So, here we can see that since we are not interested in increasing the performance, the inputs are applied at the rate of F reference by 2 to these two adders. That means, we have got two adders which are working in parallel, but we are applying inputs at half rate, not at the rate of F reference. That means, these adders will be operating at maybe 50 megahertz. Earlier it was operating at 100 megahertz. So, it will operate at 50 megahertz. However, here we shall be getting output at the same rate, because we are taking this output, then this output, and and the output is taken out at 100 megahertz rate from this multiplexer. But as you reduce the supply, as you reduce the operating frequency of these 16-bit adders, as we know it can operate at a lower voltage. So, we are reducing the supply voltage of these two adders by Vref by 2. We can see it is no longer Vref by 2. So, what will be the power dissipations of these parallel adder implementation? So, P parallel, what will be the power dissipation? So, we can say what will be the capacitance. We can see here the capacitance will be at least 2 times, but it may be more than 2 times, because we have more number of latches and a multiplexers. So, capacitance will increase by more than 2 times, and it has been found that the capacitance is increased by maybe 2 with respect to the C reference, it is 2.2. That means, with respect to the original circuit, the capacitance is increasing by a factor 2.2. And what about the voltage? Voltage we have seen, we have divided by 2, we have applied half the voltage. In this case, we can see, we have seen that supply voltage has been reduced by a factor of 2. So, supply Vref will be Vd by 2, Vref by 2, and frequency of operation is also reduced by a factor of 2, Vref by 2. So, for this parallel implementation, P pair is the P parallel, which is equal to 2.2 C rep into Vref by 2 square into Vref by 2. So, we can see it is equal to 2.2 by 8 into P rep. So, with respect to the original circuit, which is where the power dissipation is P reference, of course, we are focusing only on switching power dissipation, that is the one of the most dominant component. We find it is reducing by a factor of almost 1/4. This will be equal to 0.227 P reference. So, we have seen in this particular case, we have used parallelism for low power. Now, instead of using parallelism for low power, suppose our intention is to increase performance, then what will happen? Then in that case, what we shall do? We shall not go for VDD scaling. So, without VDD scaling, if you use parallelism, then you can see that area will increase by a factor of 2.2. Power dissipation also will increase by a factor of 2.2. However, the throughput will also increase by a factor of 2. That means, the throughput will double whenever we go for parallel implementation. So, this is the case where we are using parallelism for performance, obviously at the cost of higher power dissipation and also at the cost of larger chip area. But in the second case, when we are doing VDD scaling, we can see performance level we have maintained same, although we are increasing area, the power dissipation is reduced. So, in this particular case, we can say we are using parallelism for low power. That means, we are trading area for low power, keeping the performance same. So, this is the basic idea behind the parallelism, use of parallelism for low power. And you will be surprised to note that this is the basic idea behind multi-core. Nowadays, you are using multi-core processors. Why we have moved from single core to multi-core? This is the basic idea. That means, whenever we go for multi-core, the overall power dissipation is reduced. How? Let me illustrate with the help of a very simple example, multi-core for low power. So, here you can see we have used 4 multiplier cores instead of it may be ALU, but I have illustrated with the help of 4 multiplier cores. We have 4 cores, multiplier core number 1, multiplier core 2, multiplier core 3 and multiplier core 4. So, here you can see we have a multi-phase clock and multiplexer control. So, clock is 200 megahertz, original clock is 200 megahertz, but since we have got 4 cores, to each of them we are applying in 4 different phases at the rate of 50 megahertz. And then we have got a multiplexer, which of course which will operate at the rate of 200 megahertz. That clock is not applied here, but you have to apply a clock of 200 megahertz to this and take the output to the latch from the output of the multiplexer. So, this is the multi-core implementation. Now, let us see how the low power is achieved. Here the important issues are increase in overhead, limit on supply voltage, increase in leakage current. You see, these are the important issues whenever we go for multi-core. As you go from say single core to dual core, then overhead increases, because the number of buses increases, you may have to use more number of latches, more number of multiplexers of bigger size. That means, the overhead will increase. Second is there is a limit on supply voltage. Later we shall see that as we go from multi-core, go from single core to multi-core, we may reduce the supply voltage to reduce the power dissipation, but there is a limit up to which you can we can go for that. That means, the supply voltage can be reduced up to certain limit, because each processor will operate satisfactorily up to certain lower voltage. That means, we cannot reduce the supply voltage indefinitely, there is a lower limit to that. And as you keep on increasing the number of cores, there is increase in leakage current. So, that also you have to take into consideration, particularly in the present day technology, the leakage current will increase significantly. So, these things we have to take into consideration whenever we go for multi-core for low power. And here you can see how the power dissipation reduces and how the clock frequency changes as you go from say 1 core to say 2 core or to 4 core to 8 core. So, for example, for single core it is 200 megahertz operating frequency, core supply voltage is 5 volt, power dissipation is 15 watt. When it is dual core, clock frequency is 200 megahertz, sorry 100 megahertz, then supply voltage can be reduced to 3.6 volt and total power dissipation is 8.94. And for 4 core, the clock frequency is reduced by to 50 megahertz, supply voltage can be reduced to 2.7 volt, because at this voltage the processor will operate at 50 megahertz, and then total power is reduced by to 5.2 volt. For 8 core, you can see the clock frequency can be 25 megahertz with the supply voltage 2.1 volt and power dissipation is 4.5 watt. So, you see the benefit of using multi-core and how the power dissipation is reducing, and this is the basis of the present day multi-core commercial processors introduced by Intel, AMD and other processor manufacturers. And whenever we go for multi-core, actually thread level parallelism is utilized. You know that whenever we used pipelining, we use instruction level parallelism, but whenever we go for multi-core, multiple threads will be operating on multiple cores and we use thread level parallelism, but those are the topics which will be discussed in your computer architecture course. But here we can say that the shift towards multi-core is primarily for the reason of low power. That means, whenever you go for multi-core, the power dissipation is reduced, and later on we shall discuss about it in more detail. And with this we have come to the end of today's lecture. In our next lecture, we shall see how pipelining can also be used for low power. Thank you.